My name is Nate Mishner, and this is my demonstration project for MAE 535, Design of Electromechanical Systems. My goal was to demonstrate Faraday's law for electricity generation, so I built a simple DC rotating machine inspired by some other YouTube videos. So here it is. The wooden frame supports several ceramic and neodymium iron boron permanent magnets, which create a relatively uniform magnetic field between them. The rotor is a wooden pencil with axial holes, and it is suspended by paper clips. The red coil centered around the rotor are the armature windings. They have roughly 200 turns on each side. All the coils are wound in the same direction, and each end of the wire comes off the coil and runs down the shaft of the pencil to create commutator contacts. Two more paper clips serve as brushes to bring current into the armature windings. If we look down the shaft of the rotor, we can see that the commutator contacts are oriented such that they touch the brushes while the armature is about 30 degrees from horizontal. This allows the armature to generate a force when supplied with current. I originally tried to make a significantly larger machine, but poor bearings, insufficient armature windings, and a high inertia rotor made this first prototype unfeasible. In motor mode, we are illustrating this equation. Force at a conductor is equal to the cross product of the conductor vector and the magnetic field, and it's also proportional to current magnitude. In this image, we see that at the 30-degree offset angle position, several forces are generated on the copper conductors. So remember, we're conducting current right now because the brushes are touching the armature winding terminals. So here in this image, we have red dots representing current into the screen and green dots representing current out. Magnetic field lines are shown in blue. So if you take the cross product of a red conductor with a blue magnetic field line, by the right-hand rule, you get a downward force, and vice versa for the green conductors. Since some conductors are in areas of higher magnetic flux density, the forces generated by those conductors dominate, shown in larger arrows here, and a torque is generated, causing the motor to spin. We can see in this video clip that by reversing the direction of the current flow, we can switch the direction the motor spins in. This is because the forces would be in the opposite directions due to the reverse current. It's interesting to note that at the higher rotational speeds of this motor, which are right around 30 rotations per second, the camera, which is recording at 30 frames per second, starts to alias a little bit, so it gets hard to tell which direction the rotor is actually spinning in. I used an oscilloscope to examine the current and voltage in the windings. The current is shown here in green. We can use the current pulses, each corresponding to moments of commutator contact, to note the frequency of rotation. The rotational speed is limited only by mechanical losses in the system. Varying the voltage, and therefore the current, into the windings changes the speed of the motor, because you have a larger force as predicted by the last equation. With higher forces, the motor is able to overcome more mechanical loss and spin faster. As a generator, the DC machine's behavior is governed by Faraday's law of induction. Induced voltage is equal to the time rate of change of flux linkage. Flux linkage is equal to the total flux through the coil, which can be calculated from flux density and the number of coils. More coils yields more flux linkage, which results in a greater induced voltage. As the armature moves clockwise through the permanent magnet field, the magnetic flux through one of the coils, illustrated by the yellow circle, increases. An opposing magnetic field is generated by induced current in the coil, illustrated by purple arrows here. This is known as Lenz's law. Here we see the operation of the DC machine as a generator. By spinning the rotor clockwise, we can generate negative going voltage pulses on the scope. Alternatively, a counterclockwise spin induces positive going voltages. Note that higher spins will induce higher voltage spikes because the rate of change of flux linkage is higher. The voltages created by this generator are only in the range of about 100 millivolts RMS, which is not nearly enough to do something interesting like power a light or an LED. There are several ways we can improve the performance of this DC machine as a generator and as a motor. One such improvement would be to give the armature an iron core. Compared with the air core modeled in FEMM here, an iron core would significantly improve flux density in the air gap. In fact, FEMM shows an order of magnitude improvement in the magnetic field in the air gap. The smaller air gap would also improve performance. That's all I have for now. I hope you enjoyed, and thanks again to those inspirational YouTube videos.